you. So this is joint work with Peter Danziger and Masa Trade. So I'm going to start by talking about the Oberwolfach problem, and then I'll talk about how that is generalized in a sense and what work we've done on it. So the Oberwolfach problem dates to the 60s as E.T. Ringel, and it goes as follows. So we have a workshop in Oberwolfach, and say there are V people there. Now, if we look at the dining room, there are round tables, and we know the sizes of the tables, and they can seat exactly V people. So when we're talking math at dinner, we want to talk to people that we can actually interact with. So the question is, can we manage to seat the conference participants so that over the successive days of the conference, everybody gets the opportunity to sit next to everybody else exactly once? So really, this is a question about two factorizations. So a two-factor of a graph is a spanning two regular subgraph. Just notationally, I'm using the exponential notation here, m1 to the alpha 1, m2 to the alpha 2, etc., to denote how many cycles there are of each length. So this means there are alpha 1 cycles of length m1, alpha 2 of length m2, and so on. Okay. So if in our two-factor all the cycles have the same length, that's a uniform two-factor, and I'll refer to that as a CM factor. So a two-factorization of G is a decomposition of G into two factors. And thanks to Kira for defining decompositions for me, so I won't do that here, but essentially that's what we're doing. So in particular, if we have a two-factorization where every two-factor is isomorphic to a given factor f, then we'll call that an f factorization. So here's an example we've all seen before. C3 factorization of K9 is a KPS 9. All right, so what the Oberwolfach problem then is really asking, if I give you a two-factor f of kv, can you find a two-factorization of kv where each of the factors is isomorphic to f? And it's not too hard to see that for such a solution to exist, v must be odd, so that the degree of the vertices in kv is even. So if v is even, then the standard trick is to remove a one factor first. And so instead we factorize kv minus I, and this is sometimes referred to as the spouse-avoiding variant. Okay. So I'm going to let kv start, denote kv if v is odd, or kv minus I if v is even. So we're just decomposing either the complete graph or the complete graph minus a one factor, depending on the parity of v. And OPF then denotes the question of whether kv star has an f factorization. So for example, here is the solution to OP34. Here is a two-factor of K7 that has a 3-cycle and a 4-cycle. Here's another one. Here's a third one. And you can see, if I put them all together, that they use every edge in K7 exactly once. Okay, so what is known on the Oberwolfach problem? It has been quite extensively studied. So it's completely solved for uniform factors. So this dates back to around 1990. In the case that there are only two cycles in our factor, so our two-factor has exactly two components, that was finished by Tommaso in 2013. If all of the cycle lengths in our factor are even, so our two factors bipartite, that is also known. We've been doing a little bit of work fairly recently, and we have some results if there's one cycle that's of sufficiently large odd length and some extra conditions on the other cycles. It's been checked for small orders up to 40 and a complete solution is known there. In 2009, so Darren Bryant and Sharashkin found a complete solution for certain orders in a particular family of primes, and the group in Australia has also found complete solutions for V of the form 2p, where p is a prime, which is 5 mod 8. But in general, the Oberwolfach problem is still quite open. So I'm going to generalize this problem, however. Why consider only one type of two-factor? So the generalized Oberwolfach problem says we now have, say, t different two-factors, and I'm going to specify in my two-factorization of kv star how many factors I want of each type. So this is the generalized Oberwolfach problem, and in particular when all of the factors are uniform. So my factors are CMI factors. I'm going to write them, the cycle lengths, in increasing order, and I'll use this notation to say I want two factorization with alpha 1 M1 CM1 factors, alpha 2 CM2 factors, and so on. So an example here is a solution of OP9, 3922. So we have K9. The first two pictures here show C3 factors, and over here we have C9 factors, and they completely decompose K9. So necessary conditions for a solution to this problem. All of the cycle lengths will have to, in the uniform case, all of the cycle lengths have to divide the number of vertices, and the total number of factors has to be the right number. So the degree over 2, essentially. So in the case that t is 1, of course, we just get back the classic Oberwolfach problem. If t is equal to 2, then this problem is known as the Hamilton-Waterloo problem, and this is the next most extensively studied case. So where does this name come from if you haven't seen it before? If we think about the seating problem, where we're arranging dining room seating plans at a conference. So now our conference takes place in 2 venues. So on alpha 1 days, we're in Hamilton, which could be here. And on alpha 2 days, we're in Waterloo. And apparently this name actually, this variation of the problem actually came up in some back-to-back meetings of the Ontario Combinatorics Workshop in 87 and 88, held at McMaster University in Hamilton and University of Waterloo. And you can see the organizers of those conferences are people who are at this conference, Alex Rosa and, of course, Charlie Colburn. So I believe the case that was posed there was that the factors we were looking for were a C3 factor and a C5 factor. Okay, so what is known on the Hamilton-Waterloo problem? So for general two factors, not necessarily uniform, all cases have been checked up to 17 if B is odd, and up to 10 if B is even. There are some exceptional values, exceptional cases that don't exist, but it's completely known when this exists for those small orders. It's been solved when the factors are bipartite with some exceptions, and this is due to Hagfist, Brian Danziger, and Brian Danziger. I'm going to focus from now on, though, on the uniform case. So a lot of results have been done on particular cycle lengths. So if our factors are a C3 factor, a C4 factor, cycle lengths 3 and 5, 3 and 7, and so on. Those cases have been solved. When V is odd, there are also some results here: 3 cycles and 15 cycles, 5 and 15, 3 cycles and Hamiltonian cycles. And you can see that a lot of work has been done by a number of people on this problem. So there are some results looking at families of cycle lengths as well. And certain families with cyclic solutions have also been found. So we've also done a lot of work on this problem lately, and if you've heard me give a talk at a conference in the past couple of years, there's probably a good chance I was talking about the Hamilton-Waterloo problem. So we started looking at the case where our number of vertices is odd and is divisible by the product of the 2 cycle lengths. And we were able to solve this with a couple of small exceptions for alpha 2, the number of CM2 factors, and small exception in B. Simultaneously, this was being studied by Kiernan and Pastina, and they kind of came at it at a slightly different angle, and also got solutions for odd M1 and M2 cycle lengths. We generalized our result then, so when V is odd, to any case where V is not equal to the LCM of M1 and M2. And again, we have some exceptions where the number of factors of a given type is small, 1 or 3. And we have similar results for even V when M and N are odd, or excuse me, M1 and M2 are odd, although there are some extra exceptions that pop up, possible exceptions that pop up in this case. In the case that we have our cycle lengths of different parities, so again, we were looking at this at the same time as this other group, and so we have some complementary results here. We have some results when the odd cycle length divides the even cycle length, and they have also some results when these 2 lengths share a common factor, at least 3. When the cycle lengths are both even, this is known, the Hamilton-Waterloo problem has been completely solved when at least one of alpha 1 and alpha 2 is even, but neither is 1, or when one cycle length is the divisor of the other. We've been also working on filling in the case here when we can have an odd number of CM1 or CM2 factors, and we have some results in that area as well. So, what happens then if we move beyond the Hamilton-Waterloo problem if we have at least 3 different factor types? So again, I'm going to look specifically at uniform factors. So we have a CM1 factor, a CM2 factor, et cetera, up to a CMT factor. And not surprisingly, the number of results that are known is smaller. So it's been looked at when all of our factors are bipartite, so if all of the cycle lengths are even and all of the alpha I are even, so we need an even number of each factor type, that's due to Hedquist. And the result of Bryant and Danziger also gives some cases where we allow one factor to appear an odd number of times. This has also been looked at if the number of vertices is a prime power, but beyond that, very little has been done. So we started looking at using the techniques that we've used previously for the Hamilton-Waterloo problem and seeing how we could apply similar techniques in the more general case. So we've focused specifically on the case where the number of vertices is odd. And that means all our cycle lengths will be odd as well because they must divide V. And our main result says that this generalized Oberwolfach problem has a solution whenever the obvious necessary conditions hold, with some possible exceptions. Again, if we have one factor of a given type, our methods don't allow us to solve that. We need all of our cycle lengths to have a common factor, at least 3. So the GCD of the cycle length is at least 3, and V to be at least T minus 1 times L. So, how am I doing on time? Okay, so in the last few minutes, I'm going to give you a bit of the flavor of how we've constructed our factorizations. And our main tool is finding factorizations of certain lexicographic products. So in case you're not familiar with the lexicographic product, in particular, we're looking at a lexicographic product of a graph G with an empty graph on n vertices. So for example, if we have C5 here, I'm going to take the lexicographic product of C5 with K3 bar, I believe. So I'm just going to rewrite the C5. I'm going to take this yellow vertex, write another copy for ease of notation, and bring it over here so that I can write my cycle in a line. And then each vertex gets blown up into 3 vertices. And between 2 adjacent vertices on the cycle, I place K3. Okay, so think about taking the cycle and blowing up the vertices by 3. All right, and we want then, we're going to factor KV into 2 factors of given types. Again, we want to specify the number of each. So how do we do that? So I'm going to let L be the LCM of my cycle lengths, and by the necessary conditions, that's the divisor of V. I'm going to let G denote the GCD of the cycle lengths. I'll use N for L over G, and S is V over L. So I begin by taking KV, and I decompose it into these disjoint copies of KL. So we've got S copies of KL, and then I've got a KS blown up by L. So some disjoint complete graphs and a complete multipartite graph. The KL factor, what we're going to do with this is use the fact that the Oberwolfach problem has been solved for uniform factors. So I'm just going to take one of my factor types that I have enough factors of that type to play with, and I'm going to fill up these KLs with the CMI factor. And then what's left to do is to factorize this complete multipartite graph. So what I'm initially going to do with that is to factorize that into CGN factors. So I have some factorization of this graph where each of the factors looks like a disjoint union of these blown up cycles CGN. And what we need to do at this point is then to further factor CGN into the appropriate number of CMI factors for each of the cycle lengths MI. And the way that we approach that is as follows. So we construct an N by G matrix with the following properties. So each of the columns here contains each element of Zn exactly once. And then we have, if I want beta I CMI factors, then I want beta I rows whose sum is an element of order mi over g in Zn. So let's look at our example here. So this is, here g is 3, n is 9. We have C3 blown up by 9. So if I look at this first row, in my matrix I have 0, 0, 0. That has some 0, which is of order 1 in Z9. So this is going to give me a 3 cycle. And how that works, I start at the top here, and I take an edge of difference 0 from this first column. Second column says I'm going to follow with an edge of difference 0. third column, edge of difference 0. And that brings me back to my starting point. Remember, this vertex and this are identified. So I have a 3 cycle here. And then to get a C3 factor, I just develop vertically. If I look at this row, my matrix is 8, 2, 2. So I take an edge of difference 8, follow it with an edge of difference 2, an edge of difference 2. And because the sum, 8 plus 2 plus 2, is 3 mod 9, has order 3 in Z9, that means if I just keep repeating difference 8, difference 2, difference 2, I'm going to wrap around 3 times before I complete the cycle. And that gives me then a cycle of length 9. And again, I can develop vertically to give me a C9 factor. Finally, 2, 4, 4, the sum is 1 mod 9. So this is actually in itself going to give me a Hamilton factor in C39. So really then, the tricky thing for us was to figure out, well, how do we construct these matrices? And the way we actually do that, we start with an appropriate vector that lists the orders of the elements that we're aiming to get. So we start with this vector. So here we wanted 3 rows whose sum had order 1, 2 whose sum had order 3, 4 whose sum had order 9. So we want 3 elements whose sum has, that gives me these sums of order 1, 3 elements of order 1, 3 of order 3, 3 of order 9, or 4 of order 9. And moreover, we want to do this in such a way that the entries of this vector sum to 0. And then we use a theorem of Marshall-Hull, which tells us if we have an additive abelian group, in particular, we're going to use that n here. So the elements are gamma 1 through gamma n. And then I have this list of n elements that sum to 0. Then I can find a permutation of my group so if my permutation psi of my group, if I look at the elements psi of gamma I minus gamma I, they give me precisely the elements in my vector in some permuted order. So in our example, so here are the elements 1 through 9. Here's the permutation. And if we look at psi I minus I, you can see these are precisely the elements in that vector I started with, just in a permuted order. So then for each I, I'm going to take the row psi I minus I over 2 minus I over 2. And that gives me a sum of psi I minus I. If I have more than 3 elements, I can just augment this using I minus I minus I as many times as necessary. So this gives me the matrix that we use to construct the decomposition. So I'll just finish off with a few words about where this can go in the future. So one thing we've been starting to think about recently is how to get some further solutions to the Hamilton-Waterloo problem, where the cycle lengths have opposite parity. This is actually kind of the most difficult case for the Hamilton-Waterloo problem, that there is still quite a bit of work to do. Unfortunately, most of the techniques that we have for these types of problems don't really work well when we want one factor of a particular type. So when one of the alpha i's are 1, we need to find some new techniques that will give us more solutions. And also, our techniques for the generalized Oberwolfach problem required our cycle lengths to have common factors. So what can we do when the GCD of the cycle length is 1? And also, the case where V is even is still open in the generalized problem. So I'll stop there. Thank you.
before lunch. Thank you.